Welcome to Troubleshooting Fan Installations. I'm Scott Arnold, Senior Manager of Publications and Standards for Air Movement and Control Association International. On behalf of our more than 400 members worldwide, I want to thank you for joining us. We realize there's a lot to see and do at the AHR Expo. We respect and value your time and hope you find this educational session worth your while. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. This session is protected by U.S. international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. Now let's meet our presenters. As Global Technical Director for AMCA International, Nazmi Mosina is responsible for driving integrity, consistency, and quality in the establishment and application of product testing and certification requirements. Additionally, she provides leadership to achieve technical objectives and operational goals and serves as an arbitrator in technical appeals related to standards and functions. She has a bachelor's degree in electrical and electronic engineering from Bangladesh University of Engineering and Technology and a master's degree in electrical engineering from the University of Dayton. In 2020, she was named to Engineered Systems Magazine's 20 to Watch Women in HVAC list. First, though, we'll be hearing from Mark Bublitz. Mark, who is Executive Vice President, Industry Affairs for the New York Blower Company, is immediate past chairman and a past president of the board of directors of AMCA International. He joined New York Blower in 1994 with a diversity of experience, including automotive manufacturing, design of aircraft landing system simulations, and creation of data acquisition and computer control systems. Prior to being named Executive Vice President, Industry Affairs, he served New York Blower in a variety of engineering and information technology roles. He has a bachelor's degree in mechanical engineering from Purdue University and a Master of Business Administration degree from Indiana Wesleyan University.
Thank you, Scott. All right, it's Wednesday war story time. Show of hands, how many are fan manufacturers in the room? Okay, and how many are system people in the room? Okay, that's very good, actually, because if it was just the fan manufacturers that chose to hang out, it's like, look, we're just going to tell war stories and be over it, because I'm not going to give a talk on bearings, the fan manufacturer. So this is great. I'm so excited to co-present with Nazmi. She's got plenty of, and while you're scanning the learning objectives, I'm going to ask Nazmi to go up to our thought collector. So we'll get going with that in a second. So we got some interesting things to share. So the rule one of presentations is never start out with a caveat. But I know there's people in this room that have hundreds of more hours in the service field than I do. So I'm going to ask you to engage, and we'll have a little discussion. And then we're going to do a flyover of 202. 202, it's kind of this bucket of information that's been collected in the fan industry over years. And if nothing else, have you ever gotten that? Are you sure the power's on? Are you sure it's connected? Have you done that? There's a checklist in it, which is pretty handy. And it's all the things, in fact, I'll tell you a story at the end. It's a cool story about checklists. So there's the history, there's a reference. Okay, if you're going to troubleshoot, you have to have troubles. So our first exercise, Nazmi's going to record she's going to record things that you might bring to the table on what kind of troubles have you all experienced with fans and fan systems? They're all perfect? Vibration. Very good. Anything else? Noise. Good one. Power overdraw, overcurrent. Yes. Yeah. Blowing motors, blowing breakers, blowing motor starters. Never happens. All right. Thank you very much. Well, maybe we will have something to add. Fire away. Fan doesn't rotate. That would probably fall in the fan category. So, all right. Fire away.
You can't, it's moving too much air, or it's oversized.
Right, oversized. Very good. Fire. Balance. You mean like system balancing or system balancing? Very good. So fan vibration and balance. And
Low limit switches.
On pressure switches. See, once again, I did the other caveat is that I have an industrial background, so that like air handlers, God bless you guys. Okay, good stuff. So the idea was to kind of collect your thoughts and say, well, there's kind of two buckets. Either the fan's the problem or the system's the problem. Now, the bad news is for the fan manufacturers, it's always the fan that's the problem. So this is kind of a flyover of where we're going today. We'll talk about imbalance. I intentionally use two different words, imbalance and vibration, because one is a cause and the other one's the effect. There's issues with airstream, motor, drive, bearings. Really just going to do a flyover and just to maybe give you some nuggets, not necessarily solutions, because that's a problem, but give you some nuggets to think of a few things and maybe expand your inventory of, oh, it might be this. System rotation, corrosion, and system effect. And now there's actually this guy saying, what's this switch do? So you always have to, I put this slide in here because it's very sad. I've been in Europe for plus 30 years, and there's actually people that stick their hands in the outlet of fans while it's turned on and they lose fingers, as crazy as that sounds. So lockout, tag out, you guys know the stuff. If a fan, even if it's not moving, it's dangerous. Fan imbalance. So vibration is what you experience when a fan is not balanced. For New York blower, number one issue dwarfs the rest. Now, any rotating component can be a problem. It's obviously the impeller could be a problem because it's out of balance, but a shaft can be bent. Some of the industrial shafts are 6/8. If the forged shaft is 10 inches in diameter, if that has some imperfection, even keyways can mess your life up. The motor has a shaft in it that rotates. The motor has bearings. Bearings are a big issue, and then the drive can cause all kinds of problems. So there's plenty of things that can contribute to vibration issues. So here's kind of a cause and effect. We'll talk a little bit more about aerodynamic issues. It can lead to all kinds of weird performance observations. And then system effect. Actually, there was a big presentation James Conway gave yesterday on system effect, and you can actually surf YouTube. There's a whole New York blower in particular. I guess we have the market on the system effect video. But if you search system effect video, there's a whole set of videos that go through elbows and all that stuff that's in the ASHRAE handbook. That there's factors in there, but it's all with a grain of salt. In the industrial world, buildup on the wheel is a big deal. There's typically crud in the airstream. I'll show you some frankly scary pictures of impellers that kind of disintegrate. Belts are an issue. If they're not aligned, they'll create a load that is circular or pulsing with the rotation of the drive. Bearings. Amazingly enough, I've got some, I don't know if I include in this one, but there's pictures of, I've got this great band, it's balanced, and it's on sticks, So a good support structure, and then we talked about motor, sheave, or fan balance. Okay, some things you might not think of is, well, here's this impeller, and it's going around. Surely that's like it's a disc, right? Well, the problem is that shroud, that front plate, is offset from the back plate. Now, these are centrifugal wheels. So all those, in industrial applications, all those modes of vibration can be prevalent in the impeller while it's rotating in the field. So it's not just sticking a balance plate or a balance disc or a weight on an impeller that can be the issue. You can have all kinds of multi-dimensional things going on. And there's a whole kinds of different ways you can, the software analyses are getting way better at predicting these, but there's nothing better than putting a sensor on it and hitting it with a hammer to see what happens. Similarly, simple wheels like paddle wheels can have similar vibration characteristics. In particular, once again, I think this is going on because drive systems tend to use, I'm drawing a blank, it's the square wave PDS square wave approximation of a sine wave to drive a motor. Well, the problem is you're pulsing that motor on and off thousands of times a second, and on large, where there's more inertia, the bigger the motor, the bigger the shaft, bigger the impeller, the drive will ask for an action, and then the rest of the system will respond. So you'll actually create this torsional chatter. It looks like it's going around, but it's actually kind of jiggering its way around. So all that can be going on, and all these different modes can be induced. So even in air handlers, even your 10-inch fan, it may not manifest itself. But if it's a skip welded wheel or lightly manufactured, over time those could be some things that contributed to failures that why would this fail? I've got an exploded view of a fan assembly, and then in between, let's see if it works right. In between the inlet cone and the impeller, there's this we call it wheel to cone clearance. So ideally, there's a racing mechanism called smooth is fast, right? So ideally, the smoother the air can move from wherever it's coming from, around that venturi on the inlet and into the wheel. It's got to make that corner. So if the inlet's undersized or you're trying to jam too much air through that impeller, the air's going to end up beating on the back plate before it gets properly turned around. The rear of the impeller is going to get loaded, and the front of the impeller, the blade, is not, that blade is wanting to scoop something, but all the air is at the back of the wheel. So that, now you've got this semi-torsional effect on the blade. Interesting things can happen. So it's all about sizing and selection. So if that gap gets too big, and that's like a standard thing that should be in every fan installation manual that you should get, is whatever fan you buy, the A dimension there actually the gap is what's specified, but the only way to really measure it without getting your hand inside there is to set the wheel to cone, the A value there. If that is improperly set, what's going to happen is the air is going to come in, and because this is low pressure, high velocity, it's going to get sucked through this gap, and it's going to create a recirculation. And that recirculation is devastating to fan performance. So smooth is fast, a smooth inlet, it'll decrease performance, but I want to say when there's a lot of blades in there, it can cause a vibration issue. Similarly, in axial fans, ideally, that gap, that RC, the gap between the impeller blade and the housing, and when you have to have a really round tube, ideally you'd want that to be 0, because there's on a axial blade, it's basically an airfoil. There's a high pressure side and a low pressure side. The high pressure side is going to want to leak through that gap and come around on the low side. The more leakage you have, the more performance you lose. So you want that to be as tight as possible. If you can stick your hand through there, you get what you get, right? So don't stick your hand when it's running. But and then that C dimension is the gap between the blade or the back of the impeller, and if it's a vane axial fan, it has a vane which the air is ejected off the back of the blade. The vane grabs the air, redirects it, you get static pressure regain, it smooths the air out and gets it going in a generally axial direction again. It removes the rotational component from the velocity as it exits the tip of the blade. And they're good things, but they're very bad things if they're too far away from the blade that they're intended to work on. And that is a significant source of sound. So you've got this air coming off the blade, and if it smoothly transitions into that vane, you're good to go. If it bangs into that blade, you got turbulence and noise. Stall surge. So there was an excellent presentation this morning on sound where you hear that vroom sound, and whenever that's happening, it's bad. And the bigger the fan is happening on, the worse it can get. Because in smaller fans, it's a noise problem. In bigger fans, the forces are so great that it's going to cause that blade to bend, and it's just like bending a spoon back and forth. That thing's coming apart eventually. So intense vibration, it's almost too late if you get there. The noise is a good trigger, so you'll hear that rising and falling pitch, that whooshing sound. You can even have air get sucked into the inlet. So like on an axial fan, if an axial fan is pulsing, things will actually it's sucked in the inlet, but it'll actually briefly, it's possible to have the air get pushed back through the fan, as crazy as that sounds. So the system is fighting the surge condition. That's where air from the inlet and negative pressure. So why does this happen? Well, this is a typical axial air curve. So with this, the fan will respond to the system. As the pressure requirements increase, it will build pressure and reduce flow. And then typically in axial application, there's this weird skip and dupe where dip and scoop, where the airfoil properties of the blade are deteriorating. And it's basically just a flat thing, and there's all kinds of turbulence. The flow's separated from the blade. It's doing no gripping. Now the challenge is, what's happening in the fan is very briefly, these 3 points can all satisfy the pressure requirement of the system. So for a very brief moment, the fan is fully capable of responding to the system at that pressure. But then what's going to happen is, well, it's starving for air, there's something wrong, so the fan whooshes back. And what happens is, when you get this rounding, what's happening is the fan is actually literally bouncing back and forth, usually between these two. On centrifugal applications, a centrifugal fan, this curve doesn't usually go way back up. It kind of rounds off and flattens out. So bouncing between these two conditions is more prevalent than we like to hear about. So it gets back to fan selection. This section of the fan curve, I call it the meat of the curve, just 5% off peak total pressure is usually the highest efficiency part of the fan. Ideally, you'd select it there. I know you system guys, I need turn down. I got all kinds of losses I can't estimate. And that's the challenge that I think the industry, we can all get better at, is estimating these losses and how to pick better fans. Yes, sir. Mm-hmm. Thank you for triggering that. So even if you pick the fan, like I've picked the fan over here, so let's say you've picked it over there, but like in a lot of selection software, they'll be saying, hey, you're getting within 5% of peak pressure or 7%, or there's some target. You might want to push the selection down the curve a little bit, stay safe. So let's say, crazy as it is, let's say somebody comes in on a Monday morning and says, I'm going to close every damper on the entire system right now. Or let's say it's electronically controlled and somebody says, close everything. So basically, you've just pushed the system all the way back to shut off. There's leaks and things, but the point is, any disturbance of significance in the system that would cause a spike in the pressure required by the fan has the potential to push it back over the fan, back over the peak curve. And then if that's the case, literally, you open up a couple dampers or you relieve the pressure situation, and it'll find its way back. The danger is when you're close enough, and the system, just by delivering through the various manifolds and distribution center, you can have enough wobble. Fans are nasty things. They're not nasty things. They're you see the air ejecting from it. There's like 9 to 12 blades just beaten on a cutoff sheet, and there's all kinds of pulsation. That's a nasty. The velocity distribution's ugly until it gets out into the system. So it looks like a smooth curve, but life's a little more complicated. In the industrial space, these are amazing. So it does act, the impeller can actually corrode or erode, or if there's nasty things in the airstream, parts of it can disappear. The item on the left was an actual installation, and that was a cause of an impact. So there was something solid that got, and that's the ruggedest wheel, that this back plate here, that wheel is designed to literally like chop up wood chunks off of a trimmer and send all kinds of nasty things through the airstream. The item on the right was actually a misapplied fan. So that was a high performance airfoil, very high efficiency, but there were particles in the airstream. And you can see that, the inlet of the fan is over here. So what happens is those particles of the airstream, they got plenty of mass, they bang up against the back plate, they grind on, see all the paint's gone, they grind on the back of the back plate, and they literally just eat the back of the wheel out. So having the right, not just the right fan that can deliver the flow and pressure, but the right impeller design with the right blade is important. Yes, sir? That guy right there? That's a great question. It's entirely possible that was like a weld during manufacture, and it was covered up with paint, and then the paint got rotted away, and like, oops, bearings. I don't know how to answer the question. So tell me to slow down or tell me to speed up. Here's the nugget I want to leave you with, and we'll just get this out of the way. The bearings that are in fans today were not, well, they were designed to go in fans, but the original place that they were meant to be were in those roller conveyor things, like for using boxes and plates of steel. So free rolling with intermittent heavy loads or fully loaded. And you know, some of those roller things, you can watch those things roll all day, right? There's practically no friction. Fans are very difficult applications because they either have almost no load with very high speed, or in the industrial space, you'll have one bearing that has immense loads on it, vertical, and then another bearing that is almost no loads except for the belt pull. So what happened, so you got to make sure you get the right bearing in the right spot. But the other trick there is there's it's AH. So I just don't need a 1 7/16 ball bearing. I need the 1 7/16. In fact, just go to the bill of material and say what bearing, go find a replacement for that. Because the the fan manufacturers have worked specifically with, historically Dodge was genius in this area, and they developed specifically specific races with specific clearances on the balls in the race and the casing, so that you can support the speeds. So anyway, buy the bearing that came with the fan. So what's to be afraid of, or what to pay attention to? Temperature. If it's too hot, it's bad. Something's going on. It's the bearing's bound, something's misaligned, and then lubrication. So the lube, well, hopefully it comes from the manufacturer, properly lubed. And then the lubrication is important. The primary thing that we find related to lube is that they've mixed the lubrications. They'll both greases might be viable for that bearing, but if you mix them, the chemical reaction combined with whatever's going on inside the bearing will cause some nasty chemical reaction, and it'll bind up, or it'll get some sludge in there, and then the race gets scraped up and not good stuff. Once again, lubrication should ship with the fan, and then just use what the manufacturer represents. This stuff's in the checklist, just a standard routine. If the set screw bearings, which I'm happy to say are becoming less prevalent, at least as you start to get into some real horsepower, people are using center lock bearings, self-centering, locking bearing mechanisms. The set screw's torque is wrong. You've good propensity, you're going to spin that shaft, and that set screw's going to make a nice scrape all around the shaft, and it's going to be a thorn. They have to be assembly is, well, it's always important. But in some of the more sophisticated bearings that have split housing, there's a specific way to put it together, and assembly is important. Misalignment is if the bearing has the capacity to be misaligned. The way the races and the casings are set up, they're tolerant of some twist inside the housing of the bearing. But with anything, there's some max, so the idea is to have good alignment. The clearance is actually the clearance, what we mean there is the clearance between the race and the ball and the housing. So pretty much you're kind of stuck with what's delivered. But that's on the manufacturer to get that right. And that's what I was talking about, AH or C3 fit. Those are the, if the manufacturer designed or selected a specific bearing for that fan, it should be noted, and you need a replacement. Those are the couple words you need to make sure are specified. In the lubrication world, in general, you should purge it, and then in the startup, it should run itself out. The bearing should self-purge, and it should come into some level. Moisture is bad. Anytime it gets in the lube, that's a problem. Don't mix types, dirt, all that standard kind of, it's rotating equipment, it's got lubrication. Anything that gets in there other than the lube is bad. All right, shipping damage, and then there's actually a lot of times it's like, we don't know why it failed, but we'll just put new bearings on it and see what happens. Talked about misalignment. And then this is kind of a big one for industrial fans in particular. But if your fan's going to sit around, having some humidity control or even tarp coverage, whatever. But the big deal is rotate it just go out and spin the wheel every couple weeks. And then every month, just purge the bearings, push the old stuff out and put new stuff in. Do you guys have bearing war stories, or is this ringing a bell? I am kind of cruising. Okay. I'm going to hand this over to Nazmi.
Yes,
Nazmi
thank
has
you.
extensive experience in the laboratory with motors and drives and testing, so have at it.
Thank you for joining us. I hope you're having a good time with HR show. I didn't expect that many. I thought maybe 5 or 6 people going to be here, and look like nobody lives north side of this country. Anyway, before I start, I would like to set up the stage saying it's very uncomfortable for me to share the stage with a giant. I mean, not physical, but a giant in the industry. Okay, so I know nothing compared to what he knows. So I'm just presenting what is in 202. So
Don't let her fool you.
okay, so motor and drives. The problem is what? Doesn't work, right? So it doesn't work. There's no motor manufacturer here, I believe. Okay, so I represent fan manufacturer, and then some of our members are also motor manufacturer. And then smoke. That means something is burning, right? Turn it off. Do not think, just switch off. And then no noise from the fan and no airflow. That means something must not be hooked up correctly. It happens quite a bit in our lab. I don't know, does anybody know about AMCA, what we do? So AMCA is the not-for-profit association, as Scott mentioned. We have a lab, we test manufacturers' fan, and the technicians run through very interesting stories sometime. And then this is how we learn stuff. Okay, so usually what happened, motor and drive, it's a faulty connection, right? Under our voltage or the voltage imbalance, then what is the remedy? Balance single phase load and then transformer and this. I'd like to mention something here. It's ASHRAE 222, the standard. There's a motor and VFD test standard, and now it's very popular because fan procedure test method is in the book. That means it's regulated. Energy conservation standards is out the door, but fan have to be tested there. AMCA 210 also says how to test power drive system. The voltage between 3-phase is very tight tolerance, like it's 0.5, it's so tight. Yeah. AMCA bought like a Staco transformer that cost fortune, and that solved the voltage imbalance. Because
Can I inject something
sure,
there?
sure.
There was also an excellent presentation. You probably remember his name yesterday. I'm being an industrial guy, harmonics. Oh, it's sound. No, really, with the proliferance of these gigantic fan walls, 40 fans in a fan wall, managing the power systems to drive all those, a lot of EC motors, that was a very interesting presentation, and I learned a lot about things that I didn't even think of.
Is it Nicholas Pope, or the last one? Okay, so
yes, Nick's presentation. Yeah. So if you surf back through the stuff, that would be a good one.
It was
good one to watch.
It was presented last, right, Scott? Did I get that right? Nicholas Pope, Zillabeg, last presenter from yesterday. Yeah. Good. Thank you for sharing.
Yes.
Yeah. So another cause could be power harmonics, grounding. So part of our job is to audit other manufacturers or maybe in a lab. I have a lot of time experience, even our fan manufacturer, they build a new lab and then come back saying the power is not, our program is they test the fan at their lab, send the fan to us, we tested, it have to have a certain tolerance. We find out that power is always off, and many times that when they built the chamber or whenever they're doing the foundation, they do not ground it well. So, and that creates some kind of noise. And proper cables. So Scott mentioned I was with AMCA for some time, but last few years I was working for one of the consulting firm, and then California investor-owned utilities. They did a massive $2 million research testing motor and drive worldwide. They come up with proper cabling and their harmonics have a huge impact on the testing of the motor and drive. This is not secret. The reason I'm sharing is in actually, if you look at fan comment, then California IOUs put it in their comment about their IEC standard and what they're finding. So based on the research they did, IEC standard is looking into it, that whether they're going to be changing or not. So harmonics and proper cabling, that means from the main to the connection of the fan, the distance have an impact on the whole system. And then the rest is, you're not going to put your big 75 horsepower motor in a small room, right? So, I mean, it's all common sense. So, and then the rest is, okay. So the alignment of the drive, that is, it could be V-welt or motor and VFD. So whenever you do the motor calibration, the two shafts have to be aligned. Our lab, we have a test bench, and then the motor, where the test motor and the dummy motor, they both have that, those shaft have to be aligned. So the next portion is system effect. Mark mentioned before, yesterday, right?
Jim Conway.
Yeah, so I forgot his name.
James Conway.
Yeah, so he presented a system effect and also some troubleshooting. So it's a very good presentation. So it's listener for me. Okay, so but I would like to mention a couple things. The duct configuration, right? So whenever you have a duct, especially for axial fan, you need at least 2 to 3D diameter outlet duct. What does it do? There's a large swirl happen in the axial fan. To that swirl, to make it follow through the stream, go to the straight, you need that duct length. And if you don't do it, you'll not get a system effect.
Is that the inlet or the outlet?
Okay, so 2D, that's the outlet of the chamber. Fan.
That's where we'll go right down the
Yeah.
duct until you correct it. So I talked about the vane basically smashing that back into line, but it still needs a couple 2 or 3 duct diameters. And then if you put it on round ducting, if you have the round fan on round ducting, it'll just keep going. So you might need a flow straightener or something. But it's a whole balance of how much real estate do you guys have on the other side of the fan, and how high quality do you want that flow to resettle, so when it goes down to the next device, it's properly loaded.
And then common cause is improper inlet and outlet condition. I will talk a little bit more on the next slide. So as I mentioned, we have a lab, and then all fan are tested either AMCA 210 or ISO 5801. ISO and AMCA standard are harmonized, so they're kind of like siblings. So it doesn't matter whether you have an inlet or outlet chamber, you cause the system effect. Think about a fan, you send it to AMCA lab or your lab, you test it. It's all ideal condition, right? Think about it, you have a perfect child. There's no worries there, okay? So you have the proper condition, weather, the temperature, everything. You have the 2 to 3D duct, and then inlet. Then you get a curve like that, right? Fan and power, the fan curve, you get that. But real life is not as simple as it is, right? So for example, you have tested your fan and you create this curve. Then depending on the system effect, you may need to, in the system, you may need to have an operative. So this is the system curve. Do you guys understand the system curve? Okay, good. So it goes to here. So it's like new speed means what? More power. Because fan loss, power is cube of the speed change. So speed change, like power becomes 8 time, right? So it's gonna be more. Maybe you thought of it, okay, I need 1 horsepower motor, but actually in real life it will cost more. So over here you have a system curve, and his damper opening, there's going to be more airflow, and then over here is the more airflow. Who was saying? You were saying, right? More airflow you got? Okay, so more airflow, and then less pressure, and the power could be less. So depending on that. So let's look at the system. This is our duct, and you can see from the curve how the pressure is dropping in the duct, right? So start from here and then how different. So all we are referencing in MCA 202. If you need a copy, let us know. The MCA 202 is soon to be revision cycle. So if you found something, we should look into it, let us know that as well. So let's come back to the system effect one more time. If you have a inlet duct, inlet system effect, that means what? Less airflow is over here. So if you bought a fan for any fan manufacturer, because you are smart, you're going to buy AMCA certified product, and you said, Nazmi, your fan said 5,000 CFM, but in life, no, it doesn't. Then what do? You might have done something. It's just like you go to IKEA store, buy something, and they give you instruction. You don't do the instruction, you just put it. You're not going to get anything out of it. Anyway, of course, there are some people, they are so good, they don't even need instruction. Yeah. How many of you bake without reading the instruction? You get nothing out of it. Anyway, so let's come to work. So outlet system effect, you have it here, and then push more pressure, causing the new system curve, and then it's causing more pressure. Do you want to add anything to it?
Just to recap, it's, for a fan guy, it's a statement of the obvious. So if the system effect is on the inlet side, you haven't changed the system, so you're on the same system curve. If the system effect is on the downflow part of the fan, the fan now sees a different system. So the system curve is going to change. So upstream goes up and down the system curve. Downstream, you have a different system curve. Yes, sir?
How are the system curves on selections actually generated? Because I feel like they're kind of just made up.
I was completely prepared for this. So I was at an NEBB conference, and I'm trying to do a presentation. I'm all stressed out. And the guy goes, that system curve doesn't go to zero. There's a static head in the system, and you won't move any air until you hit that. I was like, okay. So the system curve is a quadratic equation, and that comes from the fact that friction velocity is, or friction is proportional to the square velocity. So that's what gives you a quadratic. So that's how it takes the operating point and it drills a quadratic equation in both directions. Now there's 100% of the fan manufacturers just draw it down to zero because it's easy. But for those of you that know the static head in your system and know that there's some pressure level you have to hit to get the air moving, I guess if you want, I'll draw you a special curve for that.
Yeah.
I hope I answered your question.
They did. It's just, I think, to understand, how things, how systems change, right? Like components that change in the system, and then see how you move up the fan curve. That would help you address possibly surging, right? You know, you get close to that inflection.
Well, absolutely.
You never know
yes.
if you don't have an accurate system curve.
Well, absolutely. And I kind of tying all this together to Nazmi's previous slide, I'm transparent. The manufacturer, that AMCA figure 12, that figure 12 is specifically designed so that the performance measured by that fan is its absolute best, right? Perfect inlet conditions, flanged inlet, smooth flow in, plenty of duct diameters, a big settling area, good pressure drop, and then the auxiliary fan is just used to suck the resistance of the test chamber out so you can actually get the fan down to zero. But the curve you see when you're in the fan manufacturers, it's the perfect curve, right? Now, I guess I'm going to throw it back in your lap. It's the ASHRAE Fundamentals book, understanding, duct smoothness, all the system effect stuff, elbows, smooth as fast. So any disruption is a loss. And frankly, the fan manufacturers are just not good at estimating losses in your system. We don't know a lot about coils. We don't know a lot about filters. If you want to send us a unit, we'll test it. But it's a lot of mystery. And I think one of your biggest challenges is balancing the uncertainty, what system curve am I on with cost and risk? Because if you pick too big of a fan, you're stuck. Well, too big of a fan, you're stuck. Too small of a fan, you're out of luck. So everybody tends to be a little conservative, but you're going to be burning energy, and the customer's going to be paying for that. So good luck.
What is the percentage change, like,
In
like the real life and then this, right? That's why we have the manufacturer tolerance, and we have other tolerance built in, right? Is it fair to say?
I'm just trying to think of, I'm system naive. You in the audience, I always argue, especially at New York Blower, our customers know way more about their systems. I would be very hesitant to go in and tell a customer what to do. I'm like, well, here's some fan properties, and what do you guys think? So here's
this is
some,
interesting. Yeah.
If you haven't seen the system effect, these are like some real violations. Right?
Yeah. And this was captured. So whenever you go to the fan conference or any ASHA conference, you go and see it. You see this way more than anywhere else. Yeah.
So I just take a second. Smooth is fast. So that one at the top center, you can just see that there's inlet veins in there. Probably not. They're to redirect the flow.
Doesn't look so.
There's clearly poor design.
Favorite.
Inlet boxes. Yeah, that's a classic one there. And the funny, I don't know, I hope that's not a New York Blower fan. These are real pictures. We didn't manufacture these. We discovered them. Now, with that said, in particular, speaking to the AHRI audience, I know, because I was pretty heavily involved in the whole DOE negotiation thing. I know size is a problem. I know weight is a problem. You're putting your systems on top of people, on top of roofs. So these are tough things, and I wish you the best. I encourage you to fight for as much space as you can get to make the fan do as good as it can. Because in the long run, it's that's where we're going with ASHRAE, and we want efficient systems, the whole decarbonization, and taking care of our planet. All those things fit together, and selling good products to customers and have it perform efficiently over time.
Oh, thank you. So this is a different fan. I think I mentioned this before, that how different type of fan has got different diameter, and then how that can affect the system more.
So just a fun fact.
Yeah.
If you run a fan backwards, it will generate flow. It'll operate terribly inefficiently.
Yes.
But it will generate something. And not once in a while, don't trust the rotation sticker on the fan. Bump test that thing,
Yeah. You have a video here, right?
Yeah. Let me see. So one recent technology, there we go. One recent technology advance. Who knows about motion amplification video? Oh, cool. Check this out. So the picture on the left is what we would see, right? The picture on the right is video that's been captured, and the algorithm actually finds edges, amplifies the edges, and magnifies any motion. Isn't that crazy? Look at the support structure on the fan. Now it's not really moving that much. But this is an amazing tool for finding things that would require hundreds of sensors to figure that out, and to take all those measurements and then put that into some kind of modal analysis software. So that's been, and a good service person with that set of tools can take that information and do great things. Frequently, that's the problem. Improper grouting, improper mounting. Yes, sir?
Yeah, what type of camera is that?
It's all proprietary. You have to buy the systems from these people, and I'm sorry, I can't remember the brand, but if you look up motion amplification, if you Google motion amplification, I think there's only a couple, and they've got, for at least the time now, they've got patents on all that technology, and they're holding it very close to the vest.
We're at the end. So first of all, by now you know improper installation. Then need to be certain condition and then certificate program tell you what is the duct inlet, A, like no duct, B, duct outlet, C, inlet duct, no outlet duct, D, both side duct. So it is mentioned in any fan manufacturer catalog. I'm talking about that paper. The damage in handling of transit, it happened there quite a bit. Then there will be imbalance of the wheel or any kind of, we call it ship point effect, because something happened when they shipped into our factory or anything else. The system design error, I mean, it was designed for the whole system, maybe that is something was not considered, deterioration of the system, and faulty control, we talk about it, and then poor fan selection, it might mention that it's supposed to be backward inclined, but it do something else. For example, for a house, you have to be forward curved, plus minus, but you do something other. A combination of several factors. So everything has details in Ampere 202, so let me see.
Can you forward to the QR code? And we'll handle any questions. 202's got, you know, if you ever, I think I mentioned it earlier, have you ever gotten the call, are you sure that, you know, it's plugged in, have you restarted it, blah, blah, blah. 202's got one of those checklists in the back. It's extensive, it's a lot of pages, it has all the obvious things in there, and it has some of the things that are more sophisticated. The thing I was gonna share was there's a story of a book I read called The Checklist Manifesto, and there were these doctors, and they do what's called a PICC line, where they insert an antibiotic into your system after a surgery or prior to a procedure. And it turns out that if you did this procedure, you did these 6 things all the time, you really shouldn't get an infection. Well, Johns Hopkins, they did this, it was like 30% of the hospital, these PICC lines got infected. And the nurse, they said, you know what, nurse, on your clipboard, while the doctor's doing the PICC line, just read the things off and check them as he does them, he or she does them, right? Now there's this big stink, the book goes on and on about the politics of that and the culture, but they implement, Johns Hopkins is a research institute, and they implemented that procedure. So the nurse got the clipboard, and while the doctor's doing the thing, it's like, have you done this? Yes, check, 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 check. Infections went to 0. It's an amazing book. So just that little troubleshooting list. Have we done all these things? Have we done the things in the right sequence? Have we actually bought the bearing that's on the installation checklist or the manufacturer spec? Sometimes that is the answer. Any closing questions?
So I'm a systems designer. If you held everything else constant, you selected the appropriate fan or whatever, are there particular types of fans that are less prone to vibration issues or some of the issues that we talked about, or more prone where we should be more cautious as we approach them? I guess an example would be belt drive versus direct drive. My intuition says maybe direct drive would have fewer issues.
Definitely.
Are there other things that we as systems designers should be considerate, like, hey, if I'm expecting this type of fan, now I need to be a little bit more cautious?
What comes to mind is speed kills. You know, if you're pushing the envelope or you're asking for a special exemption to, you know, I want to get this fan all the way up to 3600 and it runs at, you know, its max safe speed is 2750. So you call the manufacturer and, hey, you know, I really need this guy to run that fast. Well, it's a mod. My point is, whenever the fan is at its bleeding edge of performance, you're pushing everything, right? Any imperfection is going to be amplified. So that's one. Backward inclined fans generally, they're kind of bulletproof. Arrangement 4 backward inclined fans, airfoil backward curve. Mixed flow, yes, it's just complicated, right? It's a more complicated fan. I'm thinking through the axials. No, go ahead.
Yeah, also depends on the application, right? If you have your house, the furnace, to be forward, right? Because of the noise.
Yeah, that's a whole complication of if you're stuck, if size is an issue, a forward curve fan is going to give you the best bang for if you're stuck with size, the best performance you're going to get is with a performance fan, with a forward curve fan. But in general, a backward curve fan is going to be more efficient, consume less power, but it takes more space. So there's a couple just rules of thumb I throw out. Yes, sir.
I once had a chief engineer, great experience, tell me, good idea if you're after balancing, right? After balancing a belt-driven fan, is to switch that from an adjustable sheave to a fixed sheave, and you would take the measurement, right, that was balancing, and then do that. Is there any reason why you think that would be a bad idea, or is that not necessary? Because really, his reasoning was that over time, that adjustable sheave, that will drift.
It's not a bad idea. It's a great idea. The challenge is you're committing to the drive ratio that you replace the adjustable with a fixed shiv. An adjustable shiv is a more complicated thing, right? You're taking this screw and you're adjusting it to some setting. You have to tighten it down. It might get loose over time and tweaking. It's a more complicated thing. That's not a bad idea. But you have to buy two. You have to buy the which adjustable shiv's very expensive, but that's a good. Well, if you got 10 fans and they're all the same, you buy one and then you figure it out. Yeah, that's a good idea.
How long is that sheave last? Does it last until family?
Those are cast iron machine things. They'll last way longer than the fan.
Soft starts on a large fan we're going to procure. So because of the diesel spike on the current, the procurement's going to request a ramp-up time. And I'm thinking out loud on how your company, if you were selected to do that, you'd probably want to know what is a soft start. And then
Well.
have to document what our ramp-up time is.
So what in the industrial world, we would do is we would say, all right, what's your inertia of the impeller, inertia of the rotor, the fan shaft assembly? What's its inertia? What's it take to get it going? You'd compare that with the inertia capability of the motor, and then that would give you a minimum startup time capable of the motor. I'm just thinking off the cuff here. In theory, anything you do to slow that time down should be okay. Does it have a control on it? Because you can.
Just to reduce voltage start.
Okay. Because you can program pretty sophisticated startup sequences for motors in the drive, but I don't know if I answered your question. The fan manufacturer should be able to tell you what that number should be.
It's the motor, right?
Well, the motor has a torque capability, so it can accelerate an inertial load at a certain rate, and so you kind of need to know what the load is on the motor, and then that'll tell you how long the startup should take. And if you soft start it, so it takes longer, your current inrush should at least be below the max of the motor. Does that make sense? Okay. All right, the WR squared of the motor, and then the WR squared of whatever it is you're driving. Those who are the people you're buying that from should be able to give you those numbers. And then you should just ask them to tell you the startup time. My opinion.
If you would be willing to go back to some of those graphs from earlier, I want to ask some clarification on those.
Sure.
So those,
Which graph you are referring to?
just the one with the red segments, for example. Yeah.
Those guys? Yep.
So we have curves that are curving upwards. Those are for the system curve, which is essentially how airflow and pressure change with reference to each other. Yes. In the duct system.
Yes. Well, at the exit of the fan. Yeah.
Okay.
Yeah.
So then, what is the black curve?
Okay, so this is the fan curve. So this is the system curve, kx square. Real life, real life is the same one. And this is the fan curve, that is the airflow and pressure. So if
Okay.
everything is perfect, like it's not perfect, we all know. Everything is perfect, and this is what we call duty point, operating point. These are airflow and pressure that fan manufacturer put in the selection software or catalog, right? And the damper open, what are you doing? Adding more airflow to them, right? Then this becomes your operating point, duty point.
Okay.
So my associates, I get triggered by all these great questions, so I get conversations. Fans are pressure-sensitive devices. So if you turn the thing on, now that black line is at a fixed speed. It's at one speed. So if you just have nothing, if you just exhaust the fan out to nothingness, it will operate at that 12 flow rate. And then basically, as you stick something in the outlet, it will drive back up that curve until you eventually close it off and you get a closed off pressure. So that's the idea of a fan curve. My pleasure.
They start from left to right, that means 0 air flow to there, or lab,
We've consumed our time. Thank you so much. You've been great.